the drag force is a resistive force, just like friction. And I typically just call it drag. So the drag force, capital D, is a fluid force that is resistive. But it's resistive for different reasons. Okay, and what you're going to find here is that there are two, what am I doing? There are two categories of fluid flow. And the thing about these two categories is that you really can't separate both of them. They both have the same, they have different components of both. So the first one is known as laminar flow. And this typically is more smooth and parallel layers on top of each other. And what I mean by this, you could imagine that I have a pipe or any other thing. So I'm thinking I have this type of thing here. And what you're finding here is that I have perfect streamlines. That means if I was to put a little particle in the streamline, it would follow this line indefinitely. So that means when I draw these lines here, you could imagine that if I come in here and I put a little tiny piece of object right there, this object would follow this red line. And these lines don't cross each other. And you get sort of like this kind of smooth flow. It's non-turbulent flow. This is called idealized fluid flow. Yeah, that stuff just doesn't, right? That's an idealization. What you typically find is that in any flow, you also get turbulent. And when you're looking at turbulent flow, the big difference between these two here is that you get a mixing of the streamlines. I should have said that, by the way. So one of these guys right here is what we call a streamline. And so when I'm looking at these streamlines, they're just not so pretty. And what you're finding here is that I might have the red one do something like this. I might have, I don't know, the green maybe doing something like this, or there's this sort of like mixing of these streamlines. So these streamlines we say are chaotic and extremely difficult to solve. And you typically have to use these very gnarly equations called the Navier-Stokes equations. And these are pretty, they're unsolvable. And when they're unsolvable, what I mean here is that the only way you get solutions for these things is that you you have to throw them into computers, and then they give you some numerical number or some type of graph. But yeah, not really ideal for solving it. But this is what you find here. What you find here is that the frictional force does not depend. So if I was to compare, because this is a resistive forces, so for resistive forces like surface friction, these do not depend on speed. However, drag does. Does depend on speed. And that makes sense here. And the reason why that makes sense here, let's think about air drag, for example. So what you find here is that if you think about air drag, involves collisions with air molecules. And so you could imagine that if I have an object, let's say that this is my object here, and what's it going to do here is it's going to be falling through air that has air molecules like this. So what's going to be important here is that when you look at this thing, let's say that this is only moving at some speed v here like this. But what if I had this scenario though, right? If I come in and I do this type of thing, let me see if I can, man, I can't copy with beans here. So let's say that I have this scenario here. So as I'm looking at this scenario, what you're finding here is that this thing is now moving at a much higher speed here. What you're going to find here is that because here there's less interaction, you're going to find that the drag force in this situation is going to be small in the opposite direction. But if I'm moving faster, there's more interaction with the air molecules, and therefore the drag is larger. So these guys definitely depend on speed because you're talking about more collisions with the fluid that you're talking about. And so what you find here is that this is sort of like the rule of thumb. And the rule of thumb here, what it really tells us here is it tells us this here, that if you have laminar flow, then the drag has a tendency to depend on speed. But if you have turbulent flow, this drag changes, and it depends on speed squared. And it turns out that because so let me say this, I'm going to try to say this clearly here. What you find here, it's really, you could have a combination of laminar flow and turbulent flow. So then it's a combination of a polynomial. So it's more complicated like this. So we're talking about a really idealized situation. However, in air, this is the most common form. Water has a tendency to be more laminar, so its drag force is more related to just the velocity or the speed. So because we primarily are going to be dealing with air, you're going to find here is that in air, the drag force is this. It's D is going to be equal to 1/2 C rho A V squared. So this is the drag force. So what do I mean by the drag force? So what we want to do here is that we want to do the following thing. I want to go through each of the parameters here. So the first parameter that we should look at here is we got to look at C, which is known as the drag coefficient. And the drag coefficient, which we find here, is that it's a constant for a particular shape of an object. So if I look at this thing here, there's a table. And this table here, I just kind of copied right off of line. And you could see here, so if you look at this thing, let's look at a cylinder. So if I have a cylinder, let's say you get something like this here. So if I look at this cylinder here, and the cylinder that I'm thinking about is this guy right here, right? So this cylinder is this guy right here. So if I look at that cylinder, what I'm seeing here is that I could have a cylinder that looks something like this here. So let's say this is my cylinder and it's falling. So according to this guy, as this thing is falling through air, you're going to see that this coefficient here is 0.82. That's what its coefficient is. Now, what you can do here is that I can change the direction of this guy. And what I mean by this is that if you look at this guy here, I could take a cylinder that maybe looks like this here instead. Now, when you're looking at this cylinder, for example, so let's call this cylinder number 1, and I'll call that guy, and let's call this cylinder number 2. So as this guy falls, you can see that this will interact with more air molecules. So if it interacts with more air molecules, then what I would expect here is that this guy does what? It sees more air. So I would expect then that C2 should be greater than C1, because it's the area that tells us how much. And this guy should see less air. And so the shape tells us about that. The other parameter that you're seeing here, which a lot of people like to call P, but it's not P, it's actually a Greek symbol known as rho. And this is the density of the fluid. And for most intensive purposes, in our case, we'll probably mostly be calling that for air. And what we see here is that the density of air is 1.2 kilograms per meter cubed at sea level. The other parameter is A. This is the cross-sectional area that faces the wind. And of course, V is the speed. So one of the things that we studied in lab here is we talked about terminal velocity. So let's think about terminal velocity here for a brief moment. So what do we see here? So if I think about terminal velocity, what we find here is that what I want to do here is that I want to draw free body diagrams of the object falling through air. So what we expect here is that, let's imagine that we drop an object. Okay, so here I go. So what I'm going to draw here is I'm going to draw these things horizontally, and then you'll see me actually change how these things, and I'll label them. So what you're finding here is that I'm going to drop these green boxes in air. And so as I drop them in air, we agree that as this thing falls, its weight should not change. So this is mg. So these guys should not change at all. So here we go. So what I'm going to assume here is that this thing, I'm going to label this as 1, 2, 3, 4, 5. And I'm going to assume that V initial is 0. So that means here that the drag force should be 0. Wait a minute, if the drag force is 0, then that means this thing has to have an acceleration of g going down. But now it's moving. So this means here is that this object is encountering air drag. But because it's moving slow now, it's not encountering as much air, so therefore the air drag has built up by a little bit. But as this thing gets faster and faster, why is it getting faster? Look, there's a net force on this thing. What you're seeing here is that the air drag is getting larger. So now I have a larger air drag because I continue to speed up. Why do I continue to speed up? Because there's a net force. You could see that mg is bigger than drag. And then there's a magical point where now the air drag is equal to mg. So you're finding here is that from here to here, you're seeing that there's a net force that's not equal to 0. So therefore, the acceleration is not equal to 0. Therefore, it must be speeding up, right? So it's speeding up. But you know what? I should be real careful because what I drew here is not correct. Up to this point, it's speeding up. And so what you're finding here is that there's this point here where now I have balanced forces. After balanced forces, it's going to continue to move at constant velocity. And if it continues to move, you're seeing here is that this is sort of like you're now in dynamic equilibrium. So from here to here, you're now in the net force is equal to 0, which tells you that the acceleration is 0. This tells you here that now the velocity should be a constant, and it's this constant velocity that they call this terminal speed. So terminal speed occurs when the force of gravity is equal to d. And so now this thing moves with v equal to a constant at terminal velocity. And that speed will not change under any situation. So if I was to look at a motion diagram, what I would see here is I would see my dots. They would be getting faster and faster. So now, you know what? That's a little bit too much for me. How about if I do it like this, and then I do it like this? And so right here, here's my point 1, 2, 3, 4. So you can see that my speed is increasing. It's increasing. And then after this, the speed is going to be the same no matter what. So then the length of these vectors, this is where now this is terminal velocity at this point. It will not speed up because the acceleration is 0, whereas here, the acceleration is not equal to 0. That's what I mean by drag force.